Okay, yo, it's time for another amplifier repair video. Pretty big one on the bench today. We have an Atomic 5K AT-5000.1D. This is a pretty heavy amplifier, decent 5K, should do rated power or slightly more. Got twin inputs on the side as well. Obviously no onboard fuses, as a standard with these big amplifiers. You can't fuse 5K with flipping blade fuses. So let's have a look what we've got going on inside this one then. Now this is a pretty old girl, this has been around a little while. This has changed hands many times according to the owner. And she stank. She stinks like hell. We have lots of burnt bits and pieces going on in here. So let's take my other camera right here and let's go and have an investigation and see what we got. So initial thoughts then, let's find the source of this stank. If we have a look over here, we can see that the power supply section, which is always nearest to the power inputs, there are some pretty janky looking burnt gate resistors here. Board looks pretty burnt over here, so this will be the cause of the smell. Most of the time when an amplifier gets smoky and stanky, it's because the power supply has gone down, because what happens is there's no protection over the power supply MOSFETs from the battery input. So if one of these power supply MOSFETs goes short, then all it does is it just becomes a kind of resistor in between the positive live and the ground of your battery. So your battery will just cook the shit out of it until you pull the cable, or until your inline fuse blows, or until the MOSFETs actually short open, if they just blow open and stop becoming part of the circuit altogether. So we've got some burnt sections over here. Also, this side is burnt as well, so pretty much the whole power supply is burnt to fuck. And the cause of that, obviously, we will find at some point. Looking on the output section, visually, doesn't seem to be any burnt gate resistors for the output MOSFETs. This doesn't mean that the output section is okay. The output section, because it's controlled by the amplifier, the power supply, if the output section goes short, then the protection circuit will kick in and shut down the output section. And sometimes it kicks in quick enough to save the power supply, and sometimes it doesn't. So in this case, it didn't. So we either have just a power supply repair to do, or we have power supply and output section. So this board is a pretty standard board. It's the same architecture as pretty much all the amplifiers I've seen of this power range, really. It's a standard sort of Korean style board, and we've got the common driver board here, which you will have seen in a few of my other videos, which uses four 21844S driver ICs, a bunch of Zener diodes, use the 072C IC on there as well to generate the drive waves, and yeah, pretty basic stuff. It's a pretty generic board, but they do work well. This board design is getting on for 10-15 years old now, though. It was designed when MOSFET technology was in an inferior state to where it is these days, which is why you find the Brazilian amplifiers using modern technology, modern MOSFET technology, can produce amplifiers that do this power but are half the size, or maybe even smaller. So yeah, old board design, but it's tried and tested and has most of the bugs ironed out, depending on the build quality of said board at the time. So yeah, let's get cracking then, and we're going to take all of these clips off. I hate amps with these clips. They are far more annoying than the ones that have the screws that hold these things on. So to take these clips off effectively, what we want to do is take an Allen key that is thick enough to be able to bend, but not too thick that it doesn't fit in the hole. Let's try this one. So just want to take an Allen key here, pop it in the hole here. Now don't be afraid to pull quite hard, as they will require some effort to take off. Let's leverage it back, and there we go, clips off. And you sometimes, especially the first time you're doing this, you'll feel like you're breaking it, but you're not. It's just these clips are pretty rugged, and you have to put some pressure to get these things off. So just go along the whole board, and a lot of the time when it kicks back, you'll end up smashing your thumb on the transformer here, but that's just part of amplifier repair that you have to get used to. Yeah, so now we've taken the amp out of the case, you can see the extent of some of the damage here on the power supply. And when these short, like I said, they just get cooked by the battery or the power supply in the vehicle. And I feel a fitting song to go along with this. good things to check on these amplifiers when you first take them apart is these four middle things that you might mistake for FETs initially, and there's another 4 on the other side as well. These are the rectifiers, so these will change the alternating current from the transformers in the power supply section into a positive and negative DC rail voltage. And in upright amplifiers like this, sometimes if the amplifier doesn't have middle mounting screws along the board, which this one does, so it's fine, but if it doesn't, then sometimes these actually will have snapped leads at the bottom where the amplifier has warped up and down like this, and it's put pressure on these legs and they have snapped off, and that can often cause the amplifier to go down in this way. But no, we're all good on this one. Pretty good build quality on this board, so no snap leads. So in order to work out what caused this amplifier to go down, we're going to take our 39.37 inches of multiple uses and probe some of these output section MOSFETs and see whether any of them are shorted, which will have caused the power supply to come down. They might not be, it could just be a power supply failure. These FETs, they can just die over age, or could have some stupidly low voltage issues in the car that cause the power supply to be overrun. So let's see, do we have any shorts on the output section? So we'll have a few different banks here. Looks like we've got 4 banks of 4. So we've got 4 FETs, 4, 4 and 4, and each bank is driven by a separate IC. So we might have 2 high, 2 low. I think that's probably what it is. We've got a bank of 2 high, 2 low. Let's see whether any of these are shorted. We're just going to go ahead and take our multimeter and probe the end 2 legs, and then the first 2, and then the second and third. And we should see numbers on the screen and nothing that is close to 0, and no beeps either. So we're all good so far on this side. Okay, yeah, getting to the last FET now. So it seems that the output section potentially is okay. We won't know for sure until we repair the power supply section and get some power to the outputs and see what's going on. But usually if the output section dies and brings the power supply with it, it's because of a short circuit on the output rails. So the fact that there isn't one, that hints to the fact that it could just be a power supply fault. Now, amplifiers is less common for amplifiers just to die for no reason on the power supply, but it does happen. It can be a whole host of things. A fault in the car, like I say, stupidly low voltage run into the amplifier whilst trying to draw current, or just the age of the MOSFETs over time. They can just die. Another cause potentially is if the amplifier has ever been repaired before, whether it has been fitted with any FETs that weren't very well matched or balanced. In this case, it actually looks like the amplifier has possibly never been oh no, maybe it has. Just looking at this one here actually. Okay, so on the power supply, it's kind of hard to tell. It doesn't really look like it's been repaired before. The solder joints look pretty factory, and there is a way to tell. The solder joints either look factory or they look like they've been done by hand, really. Some of the MOSFETs in the power supply aren't from the same batch. If it's the factory that's done that, then they will have been properly matched, you would have thought, most likely. But the fact that they are from different batches may mean that they have different deterioration rates, and their specifications will change over time from different batches. So it could be that they were all perfectly matched when the amplifier went in, worked for many years, and then just over time they just went off balance and started trying to fight each other, and that's where we have a randomly blown power supply. I don't like to see different batches used anywhere in the same parallel bank for that reason, for various reasons. It's just it's just something that doesn't need to be not matched. So if you've got the choice, why would you decide not to match them? It just prevents issues further out down along the line. It just makes things a lot safer as well. So first things first then, really, with this amplifier, we're just going to remove all of these power supply FETs. We've got quite a lot of 064Ns to replace. Not going to be the cheapest of repairs, even if it's just the power supply that's dead. And what we're also going to do is replace these driver transistors in the middle, and I shall take the close-up camera because one of them does look visibly burnt. It's always a good idea to replace these driver transistors anyway when you have a blown power supply, because they don't cost much, and they can be dead. They can be damaged without necessarily showing as dead straight away. So you see this one here. You can see there that it has some physical damage on the back where it's blown open, and I would imagine the others are probably pretty damaged as well. So This chip here, this is the 494, a pretty common chip. You might see a 7500, which is pretty much the same thing. This IC chip is responsible for dealing with the majority of the power supply protection circuit, and also the power supply operations. So the pulse width modulation wave, which it comes out of pins 9 and 10 on this IC, then gets buffered by these driver transistors before going to the 064N MOSFETs. So usually the chip is fine because it's buffered by these driver transistors. So if these die, then usually the amplifier's all powered off. If this one's obviously blown open, but there's such little current, such little voltage given to this transistor by this chip that usually it's fine. Very rarely do we see a 494 that's actually been damaged. So fingers crossed, in this amplifier all we need to do is take all these drivers out, replace these, take all these MOSFETs out, replace those, and it will be up and running. This is pretty mad. You can see where this FET here, got so hot, the leg here actually snapped away from the FET anyway due to it cooking the fuck up, and it's got so hot that the solder has melted, and this leg that's come dislodged from the FET started to make its way through and is now longer than the rest of them because this is now loose. So we heat the solder up and that leg will just pull straight out. And the same happened to this one, but the leg wasn't snapped from the FET, but you can see the solder there did melt and has now reset on that one, and a couple of these. That one there as well looks a little bit sketchy, so pretty jokes. There's one more over here as well. That one's definitely melted and reset. Alright, so all the dead FETs are out, and as you can see we have pretty bad scorching of the board here to deal with. So what we're going to do is clean that up, because a lot of that can be conductive, carbonized sections of the board and crap from inside the transistor which blows out. So we're going to clean that up with some isopropyl alcohol, and then we're going to check to make sure all the gate resistors read correct. Now these ones look like they've either been covered in crap and they'll clean up nicely, or they have actually burnt themselves. Obviously we'll then go ahead and replace them. I imagine these will be 47 ohm gate resistors, as that is the common and the best ones to use for the 064N FETs. Now I've actually got some bigger gate resistors which I could drop in. If a few of these are on their way out or burnt, then I'll just replace the whole lot with the slightly bigger resistors. It doesn't really make a difference. But yeah, other than that, most of the pads look okay. There's a few that are a bit sketchy. This one here, you can see the pad has just disappeared and we've just got the board left, which is slightly carbonized, but that's not a problem. It's not interfering with anything else. Got another one here which looks kind of bad, and there's one over here as well which isn't great. But we will probably be able to get around that. If there are any traces which need to be made, connections to the top of the board, like for these transformers, then we can just use a nice thick blob of solder or an old component leg to bridge the connection from there to where it's meant to go onto the board. The area with the driver transistors looks great. I cleaned up part of the burnt area from where this one was damaged, so this is going to be pretty nice and simple to repair. The driver section, we're going to drop some 139 and 140 BD transistors in there, which are very good at driving these sorts of power supply MOSFETs. So let's get this cleaned up and see what the gate resistors are like. Right, that looks a lot better, doesn't it? So as we can see here, it's cleared up quite nicely. You can see where some of the pads were damaged, much nicer and easier now. Now these resistors were all covered in black soot before, and they haven't actually burnt themselves, although there are one or two that do look a little bit sketchy. So even if they read okay, I'm probably going to go ahead and just replace, there's 1, 2 there, and there is one over here that has lost a little bit of its outer coating, and another one here which is slightly blackened. So the way I like to check the gate resistors is actually to locate which pad on the driver transistors over here goes to each pad of the gates for the MOSFETs, and that is because then you can see any trace issues, any breaks in the trace, which are very rare, but you might as well check for them anyway, seeing as we're going to check the resistance. So first what we're going to do is see which gate driver pad is for this gate on this FET here. So this is the first FET over here. So we've got a resistor next to this FET which reads 22 ohms. So yeah, this one's obviously using 22 ohm rather than 47, not a problem. We'll replace with 22s, keep it as standard as we can. So now let's find the pad which this one is connected to on the drivers. So okay, that's this pad here. So what we're going to go ahead and do is work out where the banks are, because we want to bank match the FETs, obviously. We just want to see how these banks are laid out. So we've got 1, 2, 3, and nothing. Okay, cool. So we've got a bank of 3 here. So these are all reading pretty much 22 ohms. 22 there. 23, that's within tolerance. So then we've got a bank of 3. And I imagine we've got 12 FETs along here, so I imagine we'll have actually a bank of 6, but they'll just be split up. So we've got 1, 2, 3 on this output, and there we go, another 3 here. So we've got these 6 are all driven by the same pair of driver transistors. So this will be one bank. So these will need to be matched by batch number for the MOSFETs, and then we'll have another bank here which are split up. So we just want to make sure that the resistance of the gate resistors is the same for all of these. So let's just check this one here. 22, 22, 22, so they're all fine. So now let's find the pad for the second bank on this side then, which is this one. So we've got 22 there, 22, 22, and the last 3, 22, 22, 22. Cool. And then we just repeat the same for the other side. Like I said, a couple of these were looking a little bit sketchy, so I'm going to replace them anyway. I think I've got some 22 ohm resistors in here, so that's not a problem, just to make things safer going forward. Maybe I'll just replace all of them. They don't cost anything, do they? So yeah, fuck it, let's just replace all the gate resistors for good measure. And then what we can do is, for the first time, power the amplifier up. And when we're powering the amplifier up without the MOSFETs or the drivers in, literally the only part of the amplifier that will work is this little circuit in the middle here, which deals with power supply protection. It will usually enable the relays once it thinks everything's happy and there's no short circuits anywhere, which there's not, even though there's no outputs in. And we can read the drive waves coming from the 474 chip, going to the pads of the drivers to make sure the chip is okay, fit the drivers, then read the square waves on the gates, make sure the drivers are all working fine, and then only then can we fit the new output MOSFETs for the power supply. Yeah, look at this flipping massive mess of 22Rs. Yeah, I've got more than enough of these to replace the whole lot in this amplifier. Why have they all come off of the flipping paper? How does this even happen? It's like when you put Christmas lights away and you get them out the next year and they're all like flipping tangled to shit. Like, this was folded nicely in my drawer. Never mind. Cool, so we fitted all fresh, sparkly new gate resistors on all of these, and I also replaced one of the pull-down resistors, which are these things here. Now this one looks a little bit blackened, but it's just been covered in soot. I have limited 10k resistors laying around anyway, so no problem there. But yeah, these basically, they just pull down any residual current left on the MOSFET gate after the amplifier is powered down, and there's still power going to the source of the MOSFET. You don't want the gate to suddenly turn on and blow your FET. So yeah, all of those being replaced. Now we just need to fit some new driver transistors, and for those we are going to probably use the BD140 and 139s as stated earlier, provided I've got enough 140s left. If I don't have enough 140s left, then we will use these ones which I bought ages ago, B772s, pretty much the same thing. They're actually a bit quicker, actually slightly better than the 140s, a bit more expensive. I save them for higher premium amplifiers, which this is not really one of, but I don't think I have enough 140s left, so we're probably going to end up having to use them here. So let's see, we need 8 139s and 8 140s. Let's see what we got. Sorry, we need 4 139s and 4 140s. What the bloody hell am I going on about? Yeah, 4 of each type. And these are laid out in a configuration as follows. The 140s are on the outside with the 139s in the middle. Now if you look on the board here, the orientation is nicely laid out for us. You can see there that the original transistors were dome shaped or slightly different shape to these, and the writing on the transistor is always on the front if it has a shaped back. And so this is quite easy. We can literally just put the transistor in where the writing matches the flat front. So we're going to put 140, 139, 139, 140, 140, 139, 139, 140, and these ones will be backwards to these ones.
Great success!
driver transistors are fitted. So let's fire this up, and we will need to see some nice square waves on the gates on all of these, and then we will fit the MOSFETs. So we've got some power now applied to the amplifier in an idle state. It's off, so we've got 9.5 volts there sitting waiting. That means we also have 9.5 volts sitting on the middle pin, the source of all of these MOSFET pads, and this is where the power supply MOSFETs get their power from. So that's all good, and this board's in pretty good condition, so we shouldn't have any broken traces to these middle pads. It's pretty good. So let's put our probe then on one of these gate pads, and let's apply some remote to the amplifier and see if we get a square wave. Okay, good stuff. You can see there the pulse width modulation getting bigger. This amplifier going to full duty cycle, which it now is. The relay clicked in, as you could hear, so that means that the main protection circuit for this amplifier is done by this middle circuit here, which is the drive and power supply circuit here. The output section will have its own protection, but what it will do is it will send a high or low signal to this circuit to tell the amp to turn off. It doesn't actually have its own protection as such, it just listens, and then if it has an issue it sends a signal to this circuit to tell the amp to turn off. So cool, we have a nice looking square wave on this bank then. So let's go ahead and check that we have the same amplitude square wave on all banks. So that's 4.7 volts on this bank, 4.7 on this one, 4.7 and 4.7. So that side's looking great. 4.7, I think we'll be alright here, guys. 4.7, 4.7. Okay, fantastic stuff. So yeah, the 494 chip survived perfectly fine, as it usually does. These new driver transistors that I've fitted, they are working fine, and we are now ready to fit some MOSFETs to this amplifier to get the output section to fire up, so we can see whether there's any underlying issues that cause this amp to fail. Obviously we found no shorted MOSFETs, but there could be something weird going on. None of these inductors look like they're going to be causing an issue. They are very well seated down, good build quality here. There's no leads that can vibrate really. They're very well seated to the board. They're going to be fine. We have got some loose wires here on the transformers for the power supply section, but none of these look like they're shorted specifically. They've got a little bit of a funky bit going on this one. What I'm going to do is drop some CA glue on all of these transformers here to seal these leads down so they don't vibrate if a customer wants to mount this to a box at any point, which people like to do. So, MOSFETs then, we need 064Ns, and this uses quite a lot of them. It uses 24 in fact, and I've only got 20 in here I know of, which is kind of annoying, so I'll order a whole load of new ones of these. I could order just 4 new ones, but I might get 4 of a different batch to what I've got in here, which would not be ideal. So I'm going to go ahead and order, I don't know, 50 new 064Ns because I use them all the time. But for today, to make sure that the output section is okay, what we can do is just fit 1 FET per bank. So although there are only really 2 banks being driven by an individual driver here, there's actually there's actually 4 different banks on this side, because you have 3 here that drive this transformer, the 3 here which drive this transformer, like this, and then you have the 3 here which drive this transformer, 3 here that drive this transformer. So we need to put 4 FETs on this side. 1, 2, 3, 4. So we need 8 FETs just to temporarily solder to the power supply section to get this board up and running, so we can see what's going on with the output section and make sure it's alright. So that's not a problem. What I do for this to save doing any further damage to the board from keep soldering and desoldering, I don't put the FETs through the holes. I just drop a tiny bit of solder to the top here of the legs and have them sticking out like this. So I'll just put 1, 2, 3, 4, etc. The board's in good condition, the wires are all intact, so the power will get from top to bottom. We're not drawing any current from this, so it's just the best way to do it, and it's the safest for the amplifier board without causing too much damage from excessive heating all the time. So let's turn our soldering iron on now then, and let's fit some FETs to this power supply section. We might still have some, oh yeah, the power supply is still hooked up, so let's remove the power supply, and we'll have 9 volts sitting there. So I'm lazy, so let's just short that out to kill off the power from the capacitors. There we go, capacitor's discharged. You should really do that through a resistor, but it doesn't matter. So, soldering iron heating up, grab some solder. We're just going to lay some solder on one of these middle pads here to start with, and then take the FET, heat up the solder again, get the FET leg on there, heat the leg up, and the leg should attach to the pad. But these pads are actually very good. They're so good in fact that the solder actually just seeps through and falls down the hole. There we go. Now we've got more of a mound, so let's do that. Heat the leg. There we go. That's what I wanted to do. So we've got one on there in the first bank, and the second bank is this one. So we're going to apply some solder to this middle one here and do the same. Cool. So I'll do that for all of them, and then all you have to do is just apply a small dab of solder to the other two legs, the gate and the ground. That one there, and that one there. And now these FETs are in circuit. And we haven't gone through the holes, so we don't risk damaging the vias or the wires when we remove these. So now we've got enough power supply MOSFETs in for the amplifier to come on and power the output section. Let's apply this remote and see what happens. On the scope up here, you will see there are 3 waves that are all currently at 0, so it looks like one. We've got a probe here which will be displaying the power supply switching wave on the power supply MOSFET. And we've got 2 other probes which I have guessed, one will be rail voltage and the other will be output switch. So hopefully we get that right. I don't have to move any of them around. So let's apply some remote to the amplifier. Oh, would help if I plug the power supply back in first. Okay, so you can see there the power supply then is starting to oscillate, and it's starting to build the rail voltage in the output section. So I got that right with this. So this is obviously going too high, so I need to change the divide on that to 50 volts because it's going to be quite high. So yeah, power supply you can see there starting to switch, and this second line here you can see is starting to rise higher and higher and higher, and that is the rail voltage starting to rise. So let's have a look what we've got going on the output section. Everything pretty cold still. Yep, everything pretty cold. So the fact that the rail voltage is climbing means that we haven't got a short across any of the rails, so that's good. We're currently at 50 volts on the rail voltage, so let's get some more power supply going. You can hear it trying to come on, it's trying to switch. Okay, perhaps this power supply hasn't got enough power to get the amp to come on full duty cycle. And you can see that other wave dancing around is this wave here that was dancing around. That's the outputs. There should be a switching wave that forms there. So I don't think this power supply has necessarily got enough oomph to get this to go full switching. The green light is just flashing. Relays are clicking in and out. Is it going to be enough? 71 volts now. Okay, so I don't think this power supply has got enough. However, that little test is still valid and is still very good because what it means is that it shows us that the rail voltage is charging enough and it's not being pulled down by anything, and it also shows that the output switch is about to happen but not quite there yet. So I think that if we're safer, it's much safer now. We can apply a bigger power supply to the amplifier without the risk of it exploding first time we hit the remote, and none of these are getting hot, which is also a good sign. So yeah, let's go ahead and put a bigger power supply on and see if she comes on. Alright, second fire with a bigger power supply. Let's see what happens. Hopefully we'll go full duty cycle. You can see there, power supply coming on, amplifier. Wow, amplifier switching big time there. Oh, that's because I've got that too low. Let's go there. So yeah, we had switching on the output section there, which was good. Nice. Okay, we've got a green light. I need to change the settings on my scope from reject high frequency to reject low frequency so we can actually see what the bloody hell is going on. Come on guys. I think I need to source it on number 2. There we go. Yeah. So yeah, we can see there. Output switching wave is a little bit messy because we've got the bloody power supply wave going on. I don't usually use this this 3 probe method that much, Maybe that's a bit of a headache. Let's turn probe 3 off. So we know the power supply is all good. So let's turn it back on. Okay, that's better. So now we can see the output switching wave there. Let's turn that one off. Okay, cool. So output switch wave looks pretty good. Amplifier comes on, seems pretty happy. Let's turn probe 1 back. So that's the rail voltage. So with 12 volts of input on the bigger power supply, this now has 98 volt rail voltage. It's got a couple of little dips on there. I think that's just because this power supply doesn't find a very good ground through the scope. I think it's just a scope issue. I don't think that's anything to do with the amp itself. Okay, nice. And this one's still a little bit crazy, but probe 3 I can only get a choice of 1 volt divide or 5 volt divide, so that's why that looks a bit weird. But yeah, you can see the power supply there looks kind of weird. So I would say that these weird lines are just to do with the fact that the probe can't find a very good ground through this power supply. But no, this is good enough for checking the output wave, which looks decent. So this has been on for a minute or so now. Let's turn that off, turn the power supply off. Let's just feel for heat. So okay, they're not stone cold as they are in some amplifiers, but they're not hot either. They're just kind of like lukewarm. Sometimes these amplifiers do run slightly hotter than others, but because that is not stone cold, what I'm going to do is check the low side drive wave. I want to see what the low side drive wave looks like, and that drive wave is usually responsible for how well these outputs are driven and whether they get hot or not as they're being used. So what are we now, 36 volts on the output rail. So I need to be very careful when I'm removing this probe not to short out to the gate or anything. Okay, cool. So now let's go ahead and check the low side drive wave. And to do that, I'm going to just go on probe number 1 and turn that one off. Probe number 1, I'm going to go to AC coupling because the low side drive wave, it rides along the bottom, the negative rail voltage. So we need to AC couple it so that we bring the scope trace back to middle again. And then we need to go down to about 2 volts because it's a pretty small wave that rides along there. Now let's get the power supply back up and running. So yeah, that looks okay. It looks pretty good. There's no reason to assume that the low side drive would be causing heat there, so that's okay. Looks like the outputs are run in pairs, high side, low side, high side, low side. So okay, fair enough. If that's the case, then let's check the other low side, which is this one. Nope, that's the high side. Maybe it's 2 low sides in the middle. Yeah, 2 low sides in the middle. So that one looks okay as well. And let's go around the other side and check the 2 low sides this side. That looks alright as well. That looks right as well. So all low side drive waves look good. So output section is fully operational, up and running. These obviously just do run a little bit hotter than some amplifiers. This output section has never been repaired before, so you know it's pretty safe to say that there's no issues there from a previous repair. Yeah, they get pretty warm, but they're all getting warm equally. Usually if there's an issue with an output section or an issue with balancing on the output section or any MOSFET parallel at all, then there'll be one bank that gets hotter than the rest if there's an issue, or there'll be one FET or bank of FETs or 2 bank of FETs. The fact that these are all uniformly warm, this is quite an old amplifier. I would say that these do just run a little bit warmer than usual on idle, which is not a problem. I didn't actually look to see what this is using on the outputs. This amplifier, usually these size of amplifiers with this drive circuit use 24N40Fs. Let's see, what are we using on here? IRFP 360LC. Okay, well that might be something to do with it. I wonder if they're originals, or I wonder if this has been repaired. It doesn't look like it's been repaired before. They're all the same batch. They're all exactly the same batch. I would say this is new. Perhaps then that the 24N40Fs just run a little bit cooler. So what I could do now is actually message the customer and say, checked out the outputs, the output section runs fine, but it runs a little warm, and that's just purely due to the age of the FETs that are being used. I would recommend an upgrade to the 24N40F, which I have got a shit ton of somewhere. Yeah, I've got 2 drawers full of them. So, and they, I know for a fact from previous amplifiers, run stone cold with this drive circuitry in place. So I might shoot him a message and see whether he wants me to upgrade this output section to the 24N40Fs. Might be quite a nice thing to do, but it would be an extra cost. So if the amplifier works and runs fine with these, then he might just be obliged to just keep it the same. I'll see what he says. But for now, success. All we have to do is put the remainder of the power supply FETs in when they come in the post, all the same batch, put it back together and drop a bench test and see what power it does. So we have a parts delivery of 064Ns, got a full drawer now, so let's load this power supply up then, and we know that this is all good to go. Know the output section works pretty good, so let's load these up and then just check the output section on a bench test. I need to sort the power supplies out first, that's going to be a bit of a headache. All 24 new 064Ns fitted, and we have got the power supply on and idle, ready to go. You can see that I've got the scope on divide 50 volts, so we just got a tiny little bump there with the 9 volts of input. So let's make that a little bit, zoom in a bit so we can see the power supply wave. Now I've got the amplifier remote on a foot pedal now, so I don't have to hold the remote in the amp, which is excellent. It's far easier, so I can just put my foot on the pedal and amplifier starts to come on. So let's give this a little while then and see. Obviously this is now starting to come into operation, so I just want to give it a little bit of a go there and just check for heat on any of these, which there is not, which is all good. Should also now have some high voltage rail going on the output section, which we do, and you can see it's bumping up there with the power supply as it comes on. Nice, nice, nice. Looking good. And we can hear the coils just about to come in there with the power supply switch. A little green LED about to turn on. Now I remember from before, this amp doesn't come on, does it, on the 9 volts? Forgot about that. I just got the 9 volt supply hooked up there, so I'll plug the 12 volt one in. But that's good. I think we've got all nice looking waves on all of these. Good. So one thing that I did want to check, now obviously this power supply went down for apparently no reason. Sometimes power supply can go down when one of these transformers shorts out, but intermittently. So it will short and blow the amp, and then when you repair it, it seems to work fine and you can't see where the fault was. But actually moving around some of these coils might actually present the short circuit again in circuit. So let's grab our thing that goes on here so that I can put that onto, where shall I put it? Let's put it onto the rectifier perhaps. And let's have a look. No, maybe I want to put it somewhere that we can see if there's an issue. There we go. Okay, so let's zoom in a bit again. Okay, now what I'm going to do is play with some of these coils. Just move them around a little bit. We'll give them a wiggle. See if there are any intermittent short circuits anywhere. And obviously this set of power supply transistors is driving this coil here. So by moving this coil and having the probe linked to one of these, if the wave goes flat and doesn't look like it does now, then we know that there is a fault. Seems okay, giving it a pretty good wiggle, pretty good tap around, not being too gentle. Okay, so that one seems okay. So let's carefully remove our probe and let's put it onto the next bank of power supply FETs, which is this one here. Let's do the same again. And we just want to really give it a proper wiggle around. Make sure that there's no short circuits going to be coming anywhere. See, this one's got some loose leads on there. And what I'm going to do actually is I'm going to CA glue those down. Okay, that one seems alright. And I'm just going to do the same for the other two sides. Yeah, these all seem fine, so it's just possible that the power supply, something just went wrong with one of the FETs over time. Like I say, pretty old amp, it's been around a little while, so it can just happen. I'm going to dump some CA glue on all of these. Let's do that now actually, whilst I remember. Obviously we've got some wobbly leads here. Let's turn this off. So all we're going to do is just dump some CA all among those to stop them from moving around when the amp is subjected to vibration, and that will prevent these from shorting out. Now this glue is not cheap. I could use a cheaper CA glue on these if I wanted to, but I've got this to hand and it is probably the best stuff you can use, so why not? This is the Digital Designs Recone CA glue. That's what they use to assemble the woofers, and it's what you get as a dealer distributor for reconing their subwoofers if you are a certified repair recone technician for DD. And you can't buy this stuff on the market. It's only for industrial use. DD obviously have some access to it. It just comes in a bottle labelled DD glue. I did once have a bottle that had the actual name of the actual stuff, but that was a long time ago and I can't remember what it was. So yeah, I can't buy it privately. Just have to get it through DD, or you have to prove that you are a competent company that that can use it safely. Obviously you got little old me in my workshop sniffing in these fumes. Yeah, not ideal, but yeah, hey. I'm just going to spray the activator now, and this goes off in about 5 seconds and then you can't remove it. It goes to plastic. This is running out. Right, cool. So now I'm just going to do one last power up on the bigger power supply to get it operational for about 10 minutes or so left on idle. Going to check for heat. If I remember rightly, these do just get a little bit warm or in idle operation, which is fine. It's obviously slightly older FET design, not a problem. They're not broken, they've never been repaired, replaced, so it doesn't seem that there's an issue on the output section, so we'll leave that be for now. Yeah, plug a bigger power supply and see what happens. Bigger power supply is hooked up. Let's give it some operation. You see that's the output switching wave now. I've got this probe on, so we can see that on the screen there. Get this fan to shut up. What the hell? It's going to shut up in a minute. So yeah, I'm just going to have a last little fiddle with these transformers just to make sure that whilst it's up and running in full operation, there's no shorts or anything that cut it out. Doesn't seem to be. I think we're all good. So that's been on for about 20 seconds now. Let's just check the power supply for heat, which there is none. Fantastic stuff. And output section is yeah, it's actually still pretty stone cold. I think it needs a few minutes of operation and it just sort of like these get a little bit lukewarm. We've got quite a high voltage on these actually. We've got a peak to peak 117 volts on these, and there's not a huge number of outputs, so they're driven quite hard. Could be why. And like I said before, they are not FETs that I have seen used particularly much before in more modern amplifiers, so it could just be that they are slightly older design. So yeah, I would say a success on a component level. Let's put this back in the case and we'll drop a bench test and see what power she's doing. I've got quite good hopes for this amplifier. It has a pretty nice build quality on the board, and it's like I say, the drive circuit is the same as most amps used these days, but it was quite an early one, so pretty good for its time. I think we should see some good power from this. Whenever I'm doing a repair like this, I always take the time to take some isopropyl alcohol and clean off the heat transfer pads to the heatsink here. Usually they have old thermal paste on them which has gone hard and dry and is not effective anymore, or dust and crap has built up on them, or yeah, they just generally aren't working like they were new. Taking some isopropyl alcohol to them will just literally clean them right up and get them working to their full potential. As at the end of the day, people don't necessarily realise this when looking at amplifier repair, but really it's one of the most important parts is heat transfer, because out of the case like this 5k amplifier will struggle to do 100 watts without burning up and blowing, because the FETs have overheated. Outside of the heatsink, these FETs can only do about 2 or 3 watts each, and only when mounted properly to a heatsink can they start doing more power. And the power that they can do, the actual current which they can pass, is solely dependent on their ability to get rid of the heat that they produce from making the power or from switching the power. So we've seen how to get these clips off, but what about getting them back on? Well, it's not too difficult. All you need to do is take a hammer and chisel, or maybe a flathead screwdriver would also work. Place the clip in place, and then you want to take your chisel or flathead screwdriver and just pop it into the middle hole here, the gap in between, and hold it there in place because it will fall down otherwise. And take your hammer. Now you want to do some pretty hard blows actually to this. You don't want to be too gentle. You need it to clamp back in very hard and solid. You want the clamping to be as tight as possible. There we go. So a couple of hits and that's all it takes. If you're not sure it's gone on properly, what you can do is take it either side, give it a tap, and it shouldn't lift up either side, it shouldn't walk out, it should just stay tightly in. Okay, bench test time. Now this is my favourite part and also the most nerve-wracking part, because all your hard work could be undone in a fraction of a second if something goes wrong, but we're pretty confident because we check everything thoroughly before we put big power into this amplifier. So now we're just going to whack on the big power supplies. I haven't got the 14 volts hooked up just yet. I have got them sitting waiting to go, but I haven't actually got around to hooking them up yet fully. So we're just going to use the 12 volt supplies, and we're going to use square law to work out 14 volt power. So here goes nothing. Now the green light, which is always a good start. So obviously amplifier's powered on. Let's take our little screwdriver bit here and let's slowly increase the gain. And we're going to play a 50 Hz tone and watch when we get a click. There we go, that looks like our clip point. So we're going to hit that again. Let's do that one more time. Okay, 59.04 volts. And what was the voltage drop on that one? 11.77? Yeah, 11.77. So, okay, good stuff. That was relatively easy to bench. I was wondering whether that was actually going to cut my supplies out, but no, so the wiring seems to be pretty solid this time. So let's go ahead and take our phone and let's see what power that did then. So we have got 59.04 volts at 1 ohms. So that was 3,485 watts at 12 volts. Now what we need to do is go ahead and find the calculator and work that out for 14 volts. So we had 14.4 volts divided by 11.77, which was our voltage drop. Square that and then times that by our power that we read, 3485.72, 3485.72. So this amplifier just did 5,217 watts, corrected for 14.4 volts on the bench. Fantastic stuff. And it also did it with a wave that looks pretty decent as well. It's not got a flat top or bottom. We did this relatively low THD test. I haven't got a wave analyzer to give me the exact percentage of THD, but this works out to around about 0.5 to 1% THD. So that's the drop test out of the way. So now what I'm going to go ahead and do is hook this up to, I'm going to remove some of the dummy loads. So we've got a 1 ohm dummy load on this at the moment with 4 ohms in parallel. I'm going to remove 2 of them to give it a 2 ohm static load. And I'm also going to hook up a subwoofer like a, I don't know, 4 ohm Sony Explorer or something I don't care too much about, so that it has a reactive load and a static load to drive at the same time. And what that will do is that will give the amp some back EMF to make sure the output section is happy driving a actual subwoofer over a long period of time, but also give it a static hard load to drive, because driving a 3S Sony Explorer isn't really going to put it under much stress. So we're going to give it a 2 ohm static load plus a Sony Explorer in parallel, bring it down to about 1.6 ohms, and then we're going to leave this on for about 40-45 minutes, driving hard almost to clip point, and only then when it passes the 45 minutes without blowing will I be happy that this amplifier has succeeded and this repair was solid and it can go back to the customer. Again, thanks for tuning in. A little bit boring this one because it was just a power supply, but I've got some others on the way, like a Ground Zero 10K and some Brazilian stuff that has output section failures, so I shall cover those and they'll be a little more exciting for you. So cheers for watching and stay tuned.